Okay, so let's first start by talking about what energy is. So I feel like the majority of lectures and any type of science that you deal with always has some sort of slide that defines what energy is. Okay, so what is energy? Energy is the capacity to do work, right? So that's great. That's what energy is. But what is work exactly? So work is taking something like a box and applying a force and moving that through a distance. Okay, so work is force acting over a distance. Again, when I have to push this table across the room, that is me doing work, right? Again, energy is the capacity to do work, so I have lots of energy. All right, so what types of energy do we usually deal with? Okay, so there are a couple of different types of energy, and we're going to talk about them. So one type of energy is called potential energy, and that is the energy that is associated with the position or the composition of an object, right? So if I had a big weight, a nice little 10-kilogram weight at the top of the building, what does it have a lot of? Potential energy, right? So it's got a lot of potential energy, and again, this is the energy that is associated with the position of it, right? It's really high above the building, it wants to fall to the earth, okay? So another type of energy that we frequently deal with is kinetic energy, right? This is the energy that is associated with motion. If I push my little weight off the building, it had a lot of potential, what's going to happen to that potential energy? It's going to turn into kinetic energy, right? It's going to turn into the energy of the motion of the weight falling to earth, okay? So just in general, with respect to potential energy, what do we always want to try to minimize with respect to mechanical systems? Are weights that hang above the earth, are those super stable? No, right? So with respect to energy, systems always tend to a minimum of potential energy. The weight falls to the earth because it has a minimum of potential energy at that point in time. When it hits the earth, it's very little potential energy. A lot of that has been transformed in the form of work. Transferred in the form of work with respect to the ground. Okay? So again, potential energy is the energy associated with the position of an object, whereas kinetic energy is the energy associated with motion. Okay? Okay, so another type of energy that we encounter with respect to chemistry is something called thermal energy. Okay, so thermal energy is the energy that is associated with the temperature of a substance. Okay? All right, so with respect to thermal energy, there is kind of an overall understanding with respect to thermal energy transfer. So things that are considered hot, so let's say we have a coffee here, we consider it very hot, it has a lot of thermal energy, right? So this has lots of thermal energy. So lots. Let's say I have my hand doesn't have a lot of thermal energy because it's fairly cold. Okay, so I've got my hand, I don't want to draw it because I can't draw hands, so it's fairly cold, there's not much thermal energy. If I touch my hand to the hot cup, what's going to happen? There's going to be a transfer, right? There's going to be a transfer of thermal energy from what to what? To the cup to the hand. So in terms of temperature, right, we're seeing a transfer of thermal energy from things with high temperature to things with low temperature, right? Have you ever observed a different process where you touch something that's hot and it just sucks out energy out of your hand and it becomes even hotter? No, right? So this is kind of just like with respect to potential energy, just like the minimum of potential energy, this is kind of like just a law of nature. You're always going to see thermal energy transfer from things that have hot to cold. So just like we saw with respect to potential and kinetic energy, we transferred that energy in the form of work. With respect to thermal energy, this transfer is going to come in the form of heat. So that's what we define as heat, is this actual transfer of thermal energy from things that are hot to things that are cold. Okay? Again, that transfer is via heat. Does that transfer happen forever? So again, if I have my cold hand and I touch this hot coffee, is that going to continue forever? When does it stop? When the temperatures of the two are equal to one another, right? So when they have the exact same final temperature, then we have come to a point which is called thermal equilibrium. Okay, so again, we'll see this transfer from things that are hot to things that are cold until both things have the exact same temperature, and we are at thermal equilibrium. Okay, so that is another type of energy. So we've got potential, kinetic, thermal energy. One more with respect to chemical reactions and chemical systems is what we call chemical energy. So chemical energy is kind of like a form of potential energy. So with respect to mechanical systems and potential energy, potential energy always had to deal with the position of an object, okay? With respect to chemical energy, this is going to be energy that is associated with the positions of electrons and nuclei in various chemical species, various substances, okay? So with respect to chemical energy, we're looking at the energy associated with electrons and nuclei in our atoms and molecules. And the best way to kind of illustrate what we mean by this chemical energy is via what we call electrostatic energy. Okay, so in electrostatic energy, we kind of model this idea based on something called Coulomb's law. And this energy, or electrostatic energy, is kind of a derivative of Coulomb's law. What we're looking at here, though, is the energy with respect to two charged particles. Okay, and so we've kind of talked about various ramifications of this with respect to electrostatic interactions. So let's imagine that we have some sort of salt, something like NaCl. Right? So again, we're dealing with the chemical energy that is associated with the attraction between these two. Okay? We model this attraction via this electrostatic potential energy. So let's imagine that we have our sodium next to our chloride. Okay? And they are separated by some distance r. So when we put these guys into our little Coulomb's law, when we model them with this electrostatic potential energy, the Q's are referring to the charges. Okay, so Q1, Q2 is referring to the two charges between our two various atoms that we're dealing with. Okay, so for sodium chloride, what are the magnitudes of my charges here? +1 and -1. So I'm going to ignore right now the K because it is just a constant. When I put this in here, for the sodium we have a +1, for the chloride we have a -1, and this is going to be separated by some distance, and this is what we're referring to as R here. Okay? So again, we always want to minimize energy. Same thing with potential energy. Okay? As we bring these two closer together, what's going to be the magnitude, or what's going to be the sign of their interaction? Are they going to be positive or negative? It's going to be negative, right? So overall, we have a negative, so we're decreasing the potential energy. And what's going to happen to the magnitude of this negative value as we bring them closer together? So as this guy gets smaller, this is going to get bigger and more negative, right? So what we see is, again, this minimization of energy as we bring these two charged particles closer together. So this is how we kind of represent this idea of chemical energy. To take these guys farther apart, we're going to have to supply energy to do that, okay? But again, we kind of idealize chemical energy in the form of electrostatic energy. Okay, so potential energy, kinetic energy, thermal energy, and chemical energy. Those are all our various energy types. So now we're going to introduce you to the law of conservation of energy. This is very similar to the law of conservation of mass. So with respect to mass, what do we know about a chemical reaction? Can we create or destroy matter? No. So the exact same thing is going to happen with respect to energy. So in a chemical reaction, or in any type of process, energy can neither be created or destroyed. Okay? It can be transferred, though. Right? So what is one way that we have been transferring energy thus far in our discussion? So again, if I had, let's say, a nice little billiard ball on my table, and this guy was in motion, had lots of kinetic energy, and it was going to collide with this guy at rest, what's going to happen to the one that's at rest when the collision occurs? It's going to move, right? It's going to flow down the table. That was transfer of energy, but how did we do that? What transferred that energy between the two? That's the definition of work, right? Force through a distance. When this guy hits this guy, it transfers its energy, force through a distance. And so we can transfer energy in the form of work. So that's one way we can transfer energy between two different things. What was the other way? Put my hand on that hot cup of coffee. How did it transfer its thermal energy to me? Thermal, but what do we call that? That transfer of thermal energy was heat. So two ways that we can transfer energy is via work and heat. Okay, again, they don't disappear. The energy doesn't disappear. It just goes from one thing to another, again, via work or heat. It can also assume other forms. So what do I mean by that? If I have another little billiard ball and I have it high up in the air and I drop it, it's got lots of potential energy, right? Just like the weight on the top of the building. When I drop it, what happens? What happens to all that potential energy? Turns into kinetic energy, right? So this is what we mean by assuming other forms. When we drop this, all of this potential energy becomes kinetic. So again, energy does not get created or destroyed, it just takes another form. Okay, so we can transfer it via heat or work, or it can be essentially transformed into kinetic energy. Okay, so that is the law of conservation of energy. Now this is going to introduce us into the first law of thermodynamics. So thermodynamics is a topic that we will come back to eventually in 116. So in the second semester of general chemistry, thermodynamics is essentially going to provide us the means by which we can determine whether anything ever happens at all. Okay, so it's got this big grandiose idea behind it. We're kind of constrained in this first semester of chemistry to only talking about the first law, but again, there's more laws and we will come back to them. All right, so the first law of thermodynamics tells us that the energy content of the universe is constant. Okay, so what is the universe first off? If you imagine what the universe would be, what would you think of? Is there something outside the universe? No, right? So the universe is everything, right? So that's what we should first assume. Number one, the universe is everything. Okay, so total energy of the universe is constant, right? So this comes back to the law of conservation of energy. We know we can't create or destroy energy. It can assume other forms, we know that. It can also still be transferred, right? So if the universe is everything, is there anything with which the universe could transfer energy with? No, right? And so because there's nothing outside of the universe to transfer energy into or out of, that tells us that the total energy content of the universe is constant, okay? So you can't just make up energy. It doesn't happen like that, okay? All right, so again, what does this mean? If you are using energy right now, which you are because most of you are alive at this point in time, you're using energy to maintain that system far away from equilibrium, it has come from somewhere, right? It can't just come out of nowhere. There is no such thing as a perpetual motion machine. So for example, I am using energy to talk in front of you at this point in time. Where is this energy that I'm using? Where did it come from? Food, right? So I had a Starbucks breakfast sandwich this morning. That was number one. I also have lots of stores that I can rely on in case of starvation. That's number two. Where did the food that I ate come from? Plants, right? So I ate cows sometimes. They eat grass. Where did the grass come from? Where did it get its energy? From the sun, right? And something happens in the sun. It's like some sort of thermonuclear thing where energy is generated. But again, the purpose of this is that if you're ever using energy, it has come from somewhere. Okay, so you can't get something for nothing in terms of energy. All right, so that's great. First law of thermodynamics, the energy content of the universe is constant. It has a very nice, pleasing ring to it. It's a nice little law to live by. Okay, so with respect to energy changes, sometimes it gets confusing whether or not energy has been created or destroyed, right? So what we utilize when we are tracking energy is we utilize a system called the system and the surroundings, Okay, so the thing that we are interested in an energy exchange is what we call the system. So this could be our chemical reaction, it could be the billiard ball that we're watching, etc. Okay, so whatever we are interested in, we define as the system. Everything else with which the system can exchange energy with is what we call the surroundings. Okay, so again, this is anything our system can exchange energy with. Okay, system and surroundings. So together, what do you think they make up? So system, which is what we're interested in, surroundings is anything it can exchange energy with. Together, combined, what do you think they constitute? The universe, right? System and surroundings make up our universe. All right, so whatever happens to one, the big idea behind tracking this is whatever happens to one is going to be the opposite of what happens to the other. Because again, we're exchanging energy between our system and our surroundings. Okay, so there are a couple of different types of systems depending on what can be exchanged between them. So the first type of system that we defined is something called an open system. So in an open system, we can exchange both energy as well as matter with our surroundings. Okay, so open systems exchange energy as well as matter with their surroundings. A good example of open systems would be humans, right? We can exchange energy with our surroundings. If you touch something that's cold, we're transferring energy. What about matter? Do we exchange matter with our surroundings? Yes, right? We eat and we breathe and we do other things, right? So we can exchange both energy and matter. Another type of system that we will deal with is something called a closed system. So in a closed system, we can exchange energy, but we cannot exchange matter. So no matter with the surroundings. So this is only energy. A good example of a closed system is something like this, something like the piston that's in your car. So in the piston in your car, and I don't know how cars really work, I know there's an expansion, right? There's an expansion of a piston because of gases. This is a system where you can't actually exchange matter. The matter is going to stay in the system, but it can exchange energy in the form of doing work by expanding against that piston. Okay, so closed systems don't exchange matter, but they do exchange energy. And then finally, isolated systems cannot exchange either one, right? So in isolated systems, we can exchange energy, and we cannot exchange matter with the surroundings. A good example of an isolated system, in theory, idealized, something like this, something like a hydro flask, right? Closed, sealed hydro flask. What is the purpose of this? Why do we use it? Keeps everything cold, right? Why does it do that? In theory, in the idealized perfect version, where nothing leaks out, it's not exchanging any energy with the surroundings. So everything in there is kept cold, right? Again, this isn't perfect. If you put a bunch of ice in here, is it going to melt eventually? Yes. But again, the purpose of this, idealized, is to not be able to exchange any energy with the surroundings. That's why they produce the little vacuum seal on the outside. And if it's sealed, then it can't exchange matter. So that would be, in theory, a perfect isolated system. Okay, all right. So a couple more slides, and then I'll let you guys go for the day. Now that we have defined our types of systems, we need to talk really quickly about energy units, right? So this is a new thing that we've talked about, energy. So we need to define how we specify the amount of energy, what our units are for energy. So the unit of energy comes from the equation for kinetic energy. Does anyone know what kinetic energy, what the equation is? 1/2 mv squared. What does m stand for? Mass. So m is mass. And in the SI system of units, what is our SI unit for mass? Kilogram, right? So don't be confused. The SI system for mass is the kilogram. What is V? What is V supposed to be referring to? Velocity, right? So how do we measure velocity in SI? meters per second. It is a derived unit. So what this gives us, when we put this in for our kinetic energy equation, is 1 kilogram times meter squared per second squared. That is defined as the joule. We give this the capital J. So joule is how we measure energy with respect to SI. Okay, so the joule is actually very small with respect to the amount of energy. It's a small little value. So frequently, we will be dealing with things like kilojoules. Okay, so what do you think of kilojoules with respect to a joule? For every 1 kilojoule, how many joules do you think we'll get? 1,000 joules. So that's what's great about the metric system, right? It applies regardless. So kilojoules is just 1,000 joules. Another common way that we measure energy, unfortunately, is something called the calorie. Does anyone know what a calorie is? Tiny little c? I think this is like an English convention, like a biological thing. Little calorie is defined by the amount of energy it is required to raise the temperature of 1 gram of water 1 degree Celsius. Okay, so that's where we get our tiny little tiny calorie. In converting to joules, just note that 1 calorie is equal to 4.184 joules. You should know that conversion, just in case. What about the big C, which is what we utilize when we look at our nutrition information? What does the big C refer to? Kilocalories, right? So 1 big C is equivalent to 1,000 little calories, right? So this again illustrates why the metric system is so much more preferable, right? This prefix makes sense. What if my handwriting, which it is very bad, what if I tried to write big cal and I wrote little c, or you thought it was little c? How foolish is that? Why would 1,000 little c's be a big C? I don't understand that. It doesn't make any sense to me. So this is why this is not a smart system to go with. Okay, so then one more, kilowatt hour. It's another measure of energy. Where will you find a kilowatt hour usually? Things to do with electricity for the most part, right? So if you look at your electricity bill, you usually see how much energy you utilize in kilowatt hours. So note that 1 kilowatt hour is a gigantic amount of joules. How much money does 1 kilowatt hour cost-ish? Estimated, let's just say 30 cents, right? So again, 1 little tiny kilowatt hour, which is pretty cheap, it's only 30 cents, is equivalent to a gigantic amount of joules, okay? So this is again just trying to illustrate how tiny of a unit the joule is. Okay, all right, so those are units. What else? I'm going to take 10 more minutes, I promise. That's it. A couple more things. Okay. Internal energy. Let me get my little pencil back. I'll forget it. Okay, internal energy. We're going to define, or we're going to start talking about the energy that is important with our chemical reactions. And we start this discussion by introducing this concept of internal energy. So internal energy is defined as the sum of all of the energies of the system that we're dealing with, right? We're usually always interested in our system, and for chemistry, our system is almost always some sort of chemical reaction, okay? We define the internal energy of our chemical reaction as the sum of the kinetic and potential energies of the system, of our reaction, okay? Frequently what we will find is that the absolute value of internal energy is something that we can't obtain. Instead, we usually determine how internal energy changes in the overall process of a chemical reaction, okay? So we're going to be interested more in this change in energy, this delta E, as opposed to just E by itself. Okay, so now, internal energy is what is called a state function. And I'm going to kind of highlight what a state function is for a while because it's kind of important that you understand its definition. So for a state function, we define a state function as anything, any type of thermodynamic function whose value only depends on the final and the initial states of the system and not on how it got there. Okay, so I'm going to try to illustrate this via a nice little example. So, comparatively, altitude the measurement of altitude is also a state function, right? So when we measure altitude, again, we're frequently interested in changes in altitude. And I'm telling you that with altitude being a state function, the change in altitude for any type of reaction or any type of person is only going to be dependent on the final and the initial altitudes of that person and not on how they got there. Okay, so let's use an example to try to illustrate that. Let's say we have a hiker, right? And this hiker, we'll call this hiker A. It's at the base of a mountain, right? So initial altitude here for our little hiker, altitude initial is 0 feet. Hiker A is smart, right? Hiker A just hikes up the surface of the mountain and it gets to the top of the mountain. Nice little hiker A, where the altitude is 10,000 feet. Right? So if I wanted to calculate the change in altitude for hiker A, what would I utilize? Again, change in is final minus initial. And so if I wanted to calculate my change in altitude for hiker A, what values would I use? What is my final altitude? 10,000 feet minus my initial altitude, 0. So we get an overall change in altitude of 10,000 feet. So again, hiker A is smart, okay? All right, so now let's compare this to hiker B. Hiker B is not smart. So hiker B is on the other side of the mountain, same initial altitude, so same initial of 0 feet. Well, let's say hiker B intention is to go to the top of the mountain. Hiker B starts, and let's say hiker B gets up to about 3,000 feet. Okay, so hiker B gets up to 3,000 feet and then remembers or drops or realizes that hiker B dropped its water at 1,000 feet, right? It needs its water to get up to the top of the mountain. So what is hiker B going to do? It's going to climb back down, right? It's got to go get its water, right? So we're at 3,000 feet, and hiker B climbs back down to 1,000 feet to pick up its water, okay? Once hiker B does that, now he's ready to climb up to the top of the mountain, and so he does so to 10,000 feet, okay? So now hiker B took a different path, right? And this path has 3 separate segments to it. It has segment 1, it has yellow, which is segment 2, and it has red, which is segment 3, okay? So we're going to look at the overall change in altitude for hiker B. So for hiker B, we'll go with black. We have 3 separate segments that define its change in altitude. We have segment number 1, we have segment number 2, and we have segment number 3. What is my overall change in altitude for segment number 1? What was my initial altitude? 0. What was my final altitude for segment 1? 3,000, right? So we 3,000 final minus 0. We're going to add that to the change in altitude for segment 2, right? So we started at 3,000 feet and then we climbed back down to 1,000. So final here is 1,000 minus initial is 3,000. And then we're going to add that to our little segment 3, which we started at 1,000 feet and then hiked up to 9,000 feet. So 9,000 is, or 10,000, pardon me. 10,000 is our final, minus 1,000 is our initial. So when we add all these guys together, we're going to get 3,000 minus 2,000 plus 9,000. What is the overall change in altitude for hiker B? It's the exact same thing. It's 10,000 feet, right? So this is what we mean by a state function. It does not depend on the path that he took, right? He could have gone up and down and up and down. All we care about is where you start and where you end, okay? Internal energy is also a state function. Its path is not going to depend, or its value is not going to depend on the path that it takes, only on its final and its initial states.